For this set of problems, we're going to do a little more. In previous problems, we just found dy dx, but now we're going to find the second derivative, and we're also going to find the slope and the concavity at the selected value of the parameter. So we're going to be doing a few more things, but ultimately we're doing the same basic idea. We're going to say dy dx is dy dt divided by dx dt, and we're going to say that the second derivative is the parameter-based derivative, or the time derivative, because t is almost always time, except when it's theta, which is angle-based, ddt of that first derivative. So once we find this, we find its time derivative and divide by dx dt. So let's follow the process, and let's see how easy this can be. So what we want to do is we got to fill out this chart, so we need to find dy dt and dx dt. Now, this is like saying x is equal to t to the 1/2. So its derivative is 1/2 t to the negative half. And then the derivative of y with respect to t is simply 6, right? That's not hard to figure out. So when we plug this in, we're going to get dy dx is dy dt over dx dt. So this is negative here, so we can move it to the numerator and change it from a negative power to a positive power. And then instead of dividing by half, we're going to multiply by 2. So this becomes 12t to the 1/2, right? We multiply top and bottom by 2. That'll make this vanish. That turns into a 12. This moves to the top, 12t to the 1/2. So that's our first piece. That's sort of like our A. Now, what we want to do for B is we need to take this thing's time derivative as well. We need to say, all right, so we need to take the time derivative of dy dx. So when we take this thing's derivative, we get 6t to the negative 1/2. And then we have dx dt already. So we just have to put this together. We have to say, all right, d2y dx squared is 6t to the negative 1/2 over 1/2 t to the negative 1/2. Well, those t's to the negative 1/2s cancel, getting us 12. So this is part B. So what this tells me here, well, there's a few things. Sadly, this is going to be an annoying answer. For part C, what we do is we evaluate this at this time. So we're really saying dy dx at the point t equals 1. So this is another way to say that. So we plug in 1 here. Well, that's like 12 square root of t, right? 12 square root of t. Well, the square root of 1 is just 1, so that gets me 12, which is the same as that. And so that's your slope. Now for the concavity. Hopefully you can remember your concavity rules. If something has a positive second derivative, then it is concave up. So that is a kind of concave up situation. Now, as we move on to the second piece here, we have something, we don't have t's, we have thetas. Not a big deal. It's the same idea. So what we want to do is we want to find, instead of dx dt, we want to find dx d theta. So we're going to say, all right, dx d theta is negative 4 sine of theta. And then dy d theta is 4 cosine of theta. So then when we get our dy dx, we have dy d theta over dx d theta, which is 4 cosine divided by negative 4 sine, which is negative cotangent of theta. So negative cotangent of theta. So that's our first piece. Now for our second piece, we're going to do the same idea. We're going to say, all right, I need the theta derivative of this. So the theta-based derivative of cotangent is negative cosecant, but this is negative cotangent, so it's, cosecant squared. So this is positive cosecant squared theta, which is probably better written as 1 over sine squared theta. I don't know that, but that's sort of my intuition here. Now, then d2y, dx squared is this term divided by dx d theta, which we already have, so negative 4 sine theta. Now algebraically we can write that as 1 over sine squared times 1 over negative 4 sine of theta to get negative 1 over 4 sine cubed theta. Negative 1/4 sine cubed theta, that's part B. Now for part C, so cotangent of pi over 4 is actually just 1. So negative cotangent is negative 1. And then we need to get the concavity not t. Theta is pi over 4. So we need to plug in pi over 4 here. Now, sine of pi over 4 is 1 over square root of 2. So sine cubed of pi over 4 is 1 over 2 square root of 2. Now another way to write this is square root of 2 over 4. Hopefully that makes a little bit of sense, because when this is like 2 to the 1/2. If we cube it, we get 2 to the 3/2, which is 2 1/2, or 1 1/2, sorry, 1 whole and a half, so that's the square root. And then if I multiply both top and bottom by square root of 2, I get square root of 2 on top. This becomes a 2. 2 times 2 is 4. Hopefully you're familiar with that stuff. Obviously I didn't go through it in depth, but that's why we're not doing algebra, we're doing calculus. Anyway, so when I plug in here, I get 1 over negative 4 sine cubed pi over 4, which as seen is 1 over negative 4 times square root of 2 over 4. So you get negative 1 over square root of 2. So it's pretty simple, pretty straightforward stuff here. Actually, that's not even correct. Sorry, it's not the right answer. Now that is negative 1 over square root of 2, but the answer is what's the concavity, right? So in this particular case, what you might want to say is, okay, is this function concave up or concave down? Well, clearly it's concave down because it's negative. So that's what you want to do here. You want to say, all right, this thing's concave down. And if you were to plot this, that would be pretty simple to see, because x and y, they're actually moving around a circle. If you can't tell from what we had done before in plotting, that's going to be a circle. And you might want to know, okay, well, what's the concavity there? At pi over 4, you're going to be up, you're going to be like a quarter, an eighth of a turn, and so you're going to be concave down. So that makes sense for what we're doing. It's always nice to add a little bit of logic there. Anyway, this is the answer. Hopefully it makes sense to you. If not, rewatch it. If not, watch somebody else. Sorry, that's I guess I need to practice a little more. So try some on your own and see how well you do.